All right. Okay, so boys and girls, the other day we left off on this word problem. One of our fan favorites here. Could be one on the exam. I don't actually recall. Probably not though, but nonetheless, certainly probably a question coming up on the culminating. So it's a good one to have. It says here, a rectangular field bounded on one side by a lake is to be fenced on three sides by 800 meters of fence. What dimensions will produce a maximum area? Okay, so says that there's some sort of lake, and this fence is being bound on three sides. And they also mentioned that it is rectangular. Okay? So because this is rectangular, we have two widths and one giant footing. What we do know is that there's going to be a total of 800 meters of fencing, which tells us that the perimeter equals 800 meters. Okay? So, because it's a word problem, we can maybe say, you know, let's let L be the length. We can let W be the width. And maybe we can even let A be max area. Now, I feel like sometimes the toughest part of this type of problem is coming up with the quadratic, because we do know we're after some sort of maximum value, right? So what that might mean is that, well, we have to complete the square at some point when we're looking for a maximum, or at least find the vertex here. So in this particular scenario, like we know when you're calculating perimeter, you're just adding up all the side lengths. So in this case, perimeter is going to be, you know, width plus length plus width. And you'll notice that, you know, it's 1W plus 1 length plus 1W. And really quickly, you see that we have some like terms here. So really, the total perimeter is going to be 2 widths plus 1 length. Right? And you can also just see that in the diagram, right? Width 1 would say 2 widths there and 1 length going across. And we know that all of those, as stated before, is going to have to equal 800 meters. So we can go ahead and say, well, the 2 widths and 1 length is going to be equal to 800. And that's, so far so good. Yeah. Now, we are looking for a maximum area. And the formula for area is length times width. So at this point, we're kind of thinking to ourselves, well, what can we sub into that area, length and width, so that we can maybe get some sort of equation going? Well, if you look over back here at this perimeter formula, we're able to isolate for one positive singular variable, and that's L. So we can almost take this 2W, bring it to the other side. So we'll say something like 800 minus the 2 widths is equal to the length, which again, you know, being in grade 10, or actually at the end of grade 10, that's not really a big concept to wrap your head around. Like if the whole thing is 800 up here, right, and you take away the width and the width, of course you're just left with the length, right? Like that just kind of just makes some good sense. But the reason why we like this, I'm gonna rearrange this so that L is isolated like that on the other side, because sometimes that might feel a little bit more familiar. But this right here is our equation for L. Now, some people might say, could we have isolated W? Well, yeah, we absolutely could. We could have brought the L over instead, but then the only thing that might have been tricky is that we'd have to divide everything by the coefficient 2, right? So it's almost like when you're doing, this is a long shot, substitution. Remember substitution? There's two linear equations, and we're like, okay, which variable are we going to isolate? Because in reality, we knew that we could isolate any variable and it would work, but it was much easier to pick the variable that was, I think it was it Tiana or Ali said it? It was like the singular positive variable. No? Maybe? I don't know. Maybe it was last year. I don't know. It was here? Someone said it was like the singular, and I was like, oh, I like that. And in this case, L is our singular positive variable, so it's so much easier to isolate that one than W. So now that we have L, we can take this and substitute it into our area formula. So we'll say, okay, well, area equals length times width, but length is really 800 minus 2W, and all of that is being multiplied by the width. So all we've done here is we've replaced L with the equivalent of L. Does that make sense? Now at this point, we're going to get rid of the brackets by distributing. And this kind of probably feels a little bit weird. It's like doing the distributive property backwards. And we're allowed to. We're totally allowed to because of that communicative property. It could be this binomial times W or W times this binomial. And what we end up with is 800W minus 2W squared. And it's really important that we remember that 2W times 1W is 2W squared. And again, just like we did over here, I'm going to rearrange this so that the negative 2W squared is out front, the positive 800W goes next, because that's kind of how quadratics look. A lot of math people organize it with the highest degree first, and it goes in like a descending sort of manner. That's true for all polynomial functions. So far, so good. That's our equation. That's it. This is what we've been waiting for. This could potentially be the hardest part of the whole problem. Once you get to here, once you have this wonderful equation, all we're going to do next is, well, we're just going to complete the square. Because again, we are after that vertex. We're after that maximum value here. So we're going to take this equation. Maybe I could, we got area equals negative 2W squared plus 800W. Now, complete the square and be very careful. We're going to common factor out just the A value. Just the negative 2, not the W.
Hello. Is Carrie the service there?
She is.
Do you want to come and do services? You can keep that on?
Absolutely.
Okay, thanks very much.
You're welcome. Okay, we keep that negative 2 out front, and I always put square brackets. Whoop, so it's going to be minus 400W. Is that right? Let me go ahead and confirm that. Yes, okay. Now, I need a calculator big time. Because we know we're going to take half of this and square it. So that would be 200, negative 200 squared. It's 40,000. So area equals negative 2 square bracket W squared minus 400W. And I might run out of room here. Plus 40,000 minus 40,000. Close square bracket. Negative 2 square bracket And we end up with W minus 200 squared, right? Those first three terms factor into that binomial squared, and minus 40,000. And next is a really weird move. We're going to distribute the negative 2 to the binomial squared and the minus 40,000. So we end up with negative 2, W minus 200 squared plus 80,000. Now, if we pull out our vertex here, which we know is HK or XY, but in this case, we have width being 200, and the maximum, I'm going to put 80K, sorry, 80K, K means 1,000. Okay. So, you're not going to draw 1,000 zeros. The width is 200, the maximum area is 80,000. Now, some of you might even just say, oh, well, W minus 200, set that equal to 0, W just equals 200, and that's okay too, because that's really what we're doing. So we do know at this point now the width is 200. So if we go back to our little diagram, we know that's 200 and that's 200. So if the whole perimeter is 800, we're going to take away 200, we are left with just 400. Or you can use this. We know length is equal to 800 minus the two W's, right? W number 1 and W number 2. And since we know that they're both 200, this formula is just as good as mental math. And we clearly solve for L being 400. And that completely checks out, because at the very end here, you have a look at your diagram and you go, okay, the perimeter is 800. We got 200 plus 400 plus 200, and that is equal to 800. So it's almost like you have that little bit more confidence of like, yeah, I got this one right. So it's a question asked in words. We'll answer it in words. Therefore, the dimensions are 400 by 200 meters. What do you think? Not so bad? Questions about that one at all? Question? Say that again, please. Oh, like, so we have the max area. Divide that by the width to get the length. Yeah, I think that would work. That makes sense to me. Yeah, because if you think about it, if area equals length times width, and we know the max area is 80,000, 80,000 is equal to 200 times L divided. Yeah, I like that. That's another way to do it. That's clear. Everyone hear that? No. So Camille's saying, here, hold on here. Let's maybe snip just the end here. Well, I'll just grab those. Let's just go ahead and say we had A equals negative 2 bracket W minus 200 squared plus 80,000. That's not easy. That's big. Okay. Yeah? So Camille goes, well, if area equals length times width, yeah, and the max area is 80,000, and that's going to be length times 200, right? Because we know that width is equal to 200. So it's almost like we're subbing that into the area formula, and 80,000 equals 200L, and we just divide each side by 200, bang, bang, and 400 equals L. That could work too. I like to stick the perimeter. more my style, more my speed. Okay, cool. All right, last one here. Kind of, a lot going on here. The height of a flare above the ground is a function of the time. The height of a flare above the ground is a function of the time it is in the air. Good, good writing. An equation representing the height of the flare, h meters, above the release position after t seconds is this. This is what we wanted from all of that struggle. What is the height of the flare after 3 seconds? Okay, not so bad. Probably not the trickiest thing. What is the maximum height reached by the flare? Okay, again, not so bad. We see that word maximum and I think we know what's going on. And then determine the time the flare is higher than 80 meters. And that's the one where we're like, it's a little bit tough, but here we go. Let's break this up. We'll say, okay, part A. Let's do A right here. What is the height of the flare after 3 seconds? So what they're saying is that the value of t equals 3 seconds. So they're saying, what is the height? What is h? When t is 3, what is h? So if h equals, negative 5, t squared plus 100t. They're telling us, okay, what is h? What does h equal when t is 3? So we are just going to replace t with 3. Now, when you do this, again, be careful. If you type it in very carefully in your calculator, you can probably get away with doing it in one shot. But again, just be extremely cautious because the brackets are around 3. If you put a little x for times or multiply, it's not going to be pretty because your calculator might jumble the bed mass that's supposed to happen, maybe in the wrong order. So, you know what? Maybe I'll just take my time. Negative 5 times 9 plus 300. Before I drop the ball here, negative 5 times 9. Negative 45 plus 300. And then we get 255. Yeah? What is the height of the flare after 3 seconds? Well, therefore, the height of the flare is 255 meters. Questions about that? Okay, maybe we'll do this one in blue. What is the maximum height reached by the flare? Now, you hear the word maximum, should be something going off in your brain saying, okay, I got to complete the square. Or at least I need the vertex. Now, actually, you could do this question by solving for the x-intercepts, finding the axis symmetry, subbing that into the original equation, and getting the vertex that way, or you can just complete the square. And that's where in grade 10 math, where you kind of cross that bridge and you go, I'm not going to do all that work anymore if I know how to complete the square. So efficiency can be key here, but not the only way to do it, right? There is certainly more than one way to do it. Okay, h equals negative 5t squared plus 100t. We are after the maximum height, so we are going to complete the square really carefully. Common factor out just the a value. Negative 5, I put a square bracket, t squared minus 20t. And notice I just go right to the calculator. Like I am juggling completing the square with a coefficient for like, ooh, I'm not going to be doing 100 divided by negative 5 in my head and juggle this. No chance. Negative 5 t squared minus 20t. Oh, wait. What do we get? Negative 20 over 2 squared, negative 10 squared, 100. So we are going to plus 100 and also minus 100, close that square bracket. The first three terms factor into that wonderful binomial squared, which is really just half that b value. So negative 20, so it's half of that, minus 10, minus 100, close square bracket. Again, the weird move here, getting rid of the square brackets by distributing a negative 5 to both of the terms in there. So we end up with h equals negative 5 t minus 10 squared plus 500. So what does that tell us? Well, we can kind of pull out the vertex here, which I believe is 10 and 500. So t and h. Or I know it's h and k. Whoa, I got to be careful. I know it's h and k, but in this particular scenario, we're talking about time and height. Yeah? I'm not talking about h as in the vertex hk. I'm talking about h as in height, which is in this word problem. The dependent variable. Okay, so what does this really tell us? Yeah. The maximum height is 500 meters. Therefore, the maximum height is 500 meters. And then, like, maybe at some point I could say, and this occurs after how many seconds? Or not after, at 10 seconds. Yeah? I could see a question like this. What is the max or min value and when does it occur? I like those ones. One, because they're actually quite important. It does carry on to the rest of quadratics. And two, it's the first question on your homework. Okay, last one here. Determine the time the flare is higher than 80 meters. So what I'm going to do actually, I'm going to copy and paste this onto the next kind of the next page, because I know you have space, because I left you space on purpose, but I don't have the space. We'll be doing part C here. Now sometimes these things are best seen by drawing a little, like, not a professional, but a decent sketch, yeah? We know that this is time. We know that this is height, right? So right at 10 seconds is our vertex. And the height at our vertex was what, 500? Is that right? I'm going from the previous page here. I didn't just pull this out of thin air. We're going right out of this. We got 10, 500. So that's our maximum value. We know it's maximum facing down. Okay, we're good. It's asking us to determine the time. So what is t when height is, well, it says higher than 80 meters. Now, I think we can all understand the trajectory of a flare. So 80 meters on our y-axis, where is that about? That's 250, that's 125. It's low, right? That's like, woo. 80 meters. So really what we want to know is, what is the time here and also the time over there, such that both of these coordinates have a y value of 80. So essentially what we're doing is we want to solve for the zeros when the height is 80. Like, we don't want to solve for the zeros that are when h is 0. No, we don't want those ones. Instead of setting h to 0, we're going to set h to 80. and solve for the zeros there. So we're going to get a really small number and a really large number. So determine the time the flare is higher than or above, that's probably a better choice of words, above 80 meters. We're looking for this sort of time frame in there. So that at the beginning, which exists at point number 1, and at the end, which is at point number 2. Yeah. Sure. So let's go ahead, as part C. We're going to say H equals 80. That's what we want. So if our formula here is H equals negative 5 t squared plus 100t. Now H is 80. So we're going to sub that right in here. I'm going to replace H with it. So far, so good. Now, I kind of want to play around with this right side a little bit, but we can't actually do that until the left side, or one of the sides rather, equals 0. So we're going to bring this 80 over. 0 equals negative 5 t squared. Oh, stop writing. Good. Oh. Plus 100, okay, here we go. 100t minus 80. Minus 80 because it's positive over on the left, so it's negative on the right. Okay, so this is our quadratic that we're going to be working with, and we need to solve for the t values. That's what we need to solve for. Now, you can go in many different directions here. I'm not sure which one you'd like. However, if you're solving for t, you can either solve by factoring, or you can solve by using the quadratic formula, because both are going to, well, okay, I shouldn't say both are going to work. Factoring may or may not work, depending if the zeros are lovely or just nasty, nasty, nasty numbers, but the quadratic formula will for sure always, always, always work, no matter what, whether it's nasty numbers or great numbers. So what do you want to do? Okay, that's good. So, A, B, and C. A is negative 5, B is 100, and C is negative 80. And the quadratic formula is, I guess we'll say t equals instead of x equals. But I promise you at some point I'm going to write x equals. So just call me out on it. Negative b plus minus root b squared minus 4ac all on 2a. Okay, I gotta get some space here. Here's are the values. I got to write negative 5, 100, okay, good. So, t equals negative 100 plus minus the square root of 100 squared minus 4 times negative 5 times negative 80, all divided by 2 times negative 5. So once everything's subbed in, the first thing that I like to go to is everything underneath the square root. So, which we call the discriminant. So I go bracket, 100, close bracket, squared, minus 4, open bracket, negative 5, close, open, negative 80, close, and then I press equals, and it gives me a humongous number, which is 8,400. And this is all divided by negative 10. So maybe I'll put that in red as well. Ooh. I'll put that in, because those are the only two calculations we kind of did in that line. Now, does the square root of 8,400 actually have a decent value here? Not really. Okay, t equals negative 100 plus or minus in the square root of 8,400. Let me just double check that. Yeah, it's nasty. 91.65. Want to go 4? 15, all divided by -10. Oh, that's kind of messed me up. And this is where we plus and minus. Actually, some of you had some pretty cool strategies for the plus minus. I think it was you, Shakira. I think it was marking your test. You had that cool, like you did one on the other, like that. I split it up vertically. You split it up like horizontally, which is kind of cool. So t equals -100 plus 91.6515, all divided by -10. And over here we'll do t equals -100 minus 91.6515, all divided by -10. -100 plus 91.6515 equals, and I like to do this move here. I do like to simplify the top first. I mean, hey, if you're really confident in your calculator and you want to do it all in one shot, you really could, but you'd have to put brackets around the numerator. Then when you hit divide by -10. So be careful when you're doing it all in one shot, because the more steps you skip, the scarier this stuff can become. So we get 0.83, I'm just going to grab them all, 83485. And that's the time in seconds, yeah? Over here, this is a nice one, -191.6515, all on -10. Oh, is this just going to be positive 19.16515? Sorry, I just did that in my head, but I'm going to double check that. Nice. Lovely. So these, after all this work, I know, these are the 2 times where that flare is at 80 meters. So it's at 80 meters at 0.83485 seconds, and it is also at 80 meters at 19.16515 seconds. So if we scroll up to our really crummy diagram at the top here, we know that the time at the first 80 meters is what, 0.83485. And then the second time this thing hits 80 meters is 19.16515. So when they're asking, determine the time the flare is higher than 80 meters, that's kind of a poorly worded question. Maybe I should say, how long is the flare above these 2 time frames here? So what we're going to do, if we want the whole kind of time in here, we're just going to take the larger one, subtract it from, and we're just going to subtract the 2 times from one another here. Time above 80 meters equals 19.16515 minus 0.83485. And that is 18.3303 seconds. And because it's a word problem, therefore, the flare is higher than 80 meters for 18.3303 seconds. Sorry for my handwriting. It gets weird when it's low, which is oddly strange because I'm short. Folks, let me hear your questions about any of this stuff here. You feel good with this? Because it's kind of tough. some tough stuff in there. But if you're good with that, I mean, ooh, that means we've done a great job in here. Moving into grade 11, none of these functions will stump you. Because if you're really strong in quadratics, I feel like that is a beautiful foundation for the rest of the polynomial functions that are going to come your way. Pardon? Well, okay, yeah, good call. So I don't want you to get too hung up on a cheat sheet, but also like a cheat sheet is obviously really, really good. Definitely put down the quadratic formula on that thing. Any examples that you might want in terms of like transformations and things like that, max and min values and where they occur. Anything quadratic would be great. Remember, it's on one side of a 8.5 by 11 standard piece of paper. It could be any piece of paper, as long as it's 8.5 by 11 and it's on one side and it's handwritten. Because the moment we start going to the computer, printing things out, cutting them out, and taping them to the thing, that's where I'm like, you know. But yeah, what I can do is just give everyone a little white piece of paper. They ran out of pink paper. Cool.